have no evidence to suspect that the null hypothesis is false. No evidence to suspect H0 is false. Okay. Or other phrases you might see is, we do not reject the null, and equivalently, we do not accept the alternative. We never say we accept the null hypothesis. We never say that. And the reason for it is because from a statistics and probability standpoint, we can never prove things are equal. Okay, at least from a probability standpoint. Okay, unless the only way you can prove something is equal is if you're no longer dealing with a sample, but you somehow were able to study the entire population, then you could get a quantity for the mean of the population, and know for sure whether or not it's equal or something. Okay, but as long as you're dealing with samples, you can't prove anything about the population. We're just counting on statistics, or counting on the nature of random samples that our samples represent the population. Okay, and on the other hand, if the p-value is small, okay, so we have evidence to reject the null hypothesis, or we have evidence to accept the alternative. And so, how do we decide whether a p-value is large or small? As the researcher, or as the statistician, or whatever, we have the authority to draw a line in the sand, okay, prior to doing the test, okay? So this is something that you should do at the beginning, or somebody should tell you what number to use, okay? And this is called the significance level, or alpha. And basically, if the p-value is bigger than alpha, it's large. If the p-value is smaller than alpha, it's small. Common values of alpha, the most common is alpha is 5%. And usually to get a research article published or something, and if you're going to use some kind of test with a p-value, for your conclusion to be accepted, you probably have to show your p-value is less than 5%. Okay? A lot of times. Some places will accept larger ones. Okay? Most common choice of alpha is 5%, but equally valid is any other choice. Okay, equally valid. Other common choices: 0.01, 0.02. Sometimes you have alpha 10%, depending on the situation you're dealing with. Okay, or whatever arbitrary value you want. Okay, if for some reason you want 0.03874, fine. Okay, you might have a hard time defending why you chose that number, but sure, that's fine. Let's see. How are you guys feeling? You guys want a break right now, or can you go for another 20 minutes? I will keep going. Nobody said anything. Or did somebody say something? So, when should we pick big values of alpha or little values of alpha? Or is alpha 5%, is that good enough? Do we care? Okay. Well, the answer is, depending on the situation we're in, we might want a large alpha, or we might want a small alpha. So, but we'll talk about, but before we can make sense of what alpha means and stuff, we're going to talk about type 1 error and type 2 error, okay? So when you do a hypothesis test, you can result the conclusion you make at the very end of your hypothesis test. So you go through all of this process, and you go through all of this. The conclusion you make could be wrong, and it's not that you did any calculations wrong. This is just an inherent thing that happens because of the random nature of the world and uncertainty itself, okay? Whenever you make a conclusion, you could be wrong, okay? So, whenever you conduct a hypothesis test, okay, you could be wrong. Okay, and there's two ways to be wrong, and we were not creative in our naming of these ways, and we call these type 1 error and type 2 error, okay? Type 1 error happens when your choice is to reject the null hypothesis. You choose to reject the null hypothesis, but all along the null hypothesis was actually correct. Type 2 error, you choose not to reject the null hypothesis, but you should have, meaning the null hypothesis is really actually false. Alright, so let's say I do some test. Okay, so let's say we did that toluene in the rats and the norepinephrine. We did that thing, right? So when we did that test, we said the null hypothesis is that mu1 and mu2, that there's no difference between the rats with norepinephrine and the rats with toluene and the norepinephrine with the control rats, okay? And the alternative was that there is a difference. And we did the test, and we got p-value is between 5% and 4%. Okay? So if my alpha is 0.05, so if I choose alpha 0.05, what is my conclusion? This is the norepinephrine rats. So if I said alpha is 5%, my significance level is 5%, and my p-value is between 4 and 5%, is my p-value large or small compared to alpha? It's small. It's smaller, okay? It's not that much smaller, but it's smaller than alpha. And because alpha is just some line, and we're on the smaller side, our conclusion is, do we reject or not reject the null? We reject the null, okay? So our p-value is less than alpha, so we reject the null. We reject the null and we say we have evidence that the norepinephrine concentration of rats with toluene is different from the norepinephrine concentration of rats not exposed to toluene. That's what we say. Okay. Could we be wrong in this conclusion? Yes, we could be. What does it mean to be wrong in this conclusion? How could we be wrong? How would that have happened?
It just happens to be that 5% time.
Yeah, it means, okay, because our p-value says if the null hypothesis were true, there's only a 4 to 5% chance of us observing our data like this, okay? So we're saying, okay, 4 and 5% chance, that's low enough for us to say this null hypothesis probably is not correct, okay? But there's still a 4 to 5% chance of us getting the data, okay? So if this conclusion was wrong, then it means that what happened is there's no difference between the two rat groups in reality. But somehow, due to the random nature of randomly selecting rats and every rat being different and you don't know what kind of rat you got, okay? Because of the random nature of that and life and everything, we happened to be one of the 4 to 5%, I guess, of research groups that got this difference, which led us to believe that there is a difference when there really is not. Okay. So we just happen to be, quote, unlucky in that our samples produced a difference that led us to believe that there is a difference when there really is not. Okay. So in that situation, okay, we could have committed which type of error here? Type 1, okay? Because we rejected the null. So if you reject the null, the only type of error you might commit is a type 1 error, okay? If you reject the null, it's impossible to commit a type 2 error, okay? So if you reject the null, maybe you committed type 1 error. You're hoping you didn't, okay? But you might have, okay? So we might have committed a type 1 error. And if we did, that means there's no difference between the rats or between the rat groups, but our random samples happen to, quote, mislead us. To making the wrong decision. Okay. Yes?
How would you ever know if you made a type 1 error or
You
not?
don't. You'll
No.
never know. You'll never know. That's life. How do you know you married the right person, right? You don't know until either, you know, it works out well or it doesn't, you know? Yeah. So you don't know until either you collect more data that makes you reconsider this thing, okay? More data that counters the decision you made, or you get more data that seems to corroborate it, but you'll never, I mean, until you know all the data in the world, you'll never know whether any of your decisions are truly correct or not, okay? But we're counting on probability and statistics to kind of just say, okay, well, I'm okay with this certain amount of, I guess, risk. Yes. But yeah, you'll never truly know whether or not you made the right decision. All right. Well, what is the probability of a type 1 error in general? In any given hypothesis, what's the probability of committing a type 1 error? Not the p-value, but your... How do you make your decisions? You compare your p-value to alpha. And the probability of committing a type 1 error is the alpha that you choose. That alpha you choose is the probability of committing a type 1 error. Let's just think about that for a second, okay? So if we get alpha equal to 0.05, that means anytime I get a p-value, anytime my data says the probability of us observing this data is less than 5%, I'm going to say, that's small enough for me to say the null hypothesis is not responsible. I mean, it's random chances. I'm tongue-tied right now. Okay, so if alpha is 5%, okay, that means anytime my p-value is less than 5%, we're going to say the probability of us observing data is small enough for me to reject the null hypothesis. But there's still a 5% chance that the null hypothesis is actually true and it produced this kind of data, right? If alpha is 10%, then anytime my p-value is less than 10%, then I reject the null hypothesis. But if my p-value is 0.0999, okay, so practically 10%, it means the probability of me producing this data, even if the null hypothesis were true, is about 10%. Okay? So the probability of a type 1 error is alpha. Okay? So you're thinking, well, why would we ever want a large alpha? Why would we ever want a large alpha? Wouldn't we always just want a small alpha? Okay. Well, if you pick a small alpha, you are going to do what? A lot more and what? A lot less. If you pick a small alpha, you will be rejecting the null hypothesis a lot less. Okay? And you will choose, you will say, I don't have enough evidence to reject the null hypothesis a lot more. Okay? So if you pick a small alpha, you will reject the null hypothesis less often. Okay? And because you're rejecting the null hypothesis less often, you are increasing your risk of a type 2 error, which is when you didn't reject the null, but you should have. So by rejecting it less often, you're increasing the risk of not rejecting it when you're supposed to. I know, it feels like all these brain twister things, right? Logic. You increase your risk of a type 2 error. Okay. Yep. The type 1 and type 2 we always write with the Roman numerals for whatever reason. So you increase your risk of a type 2 error. Alright?
So if you're hoping that the alternative is true, then you would wanna have a higher.
We'll talk about when you want a large or small alpha, when you want to fix large or small alpha, and it's kind of like that, but it's not quite that, okay? So, yeah, you increase your risk of a type 2 error, and, well, actually, I have to think about what you just said, because maybe you might be right, so. You increase your risk of a type 2 error, and the probability of a type 2 error there's tedious calculations involved. Not tedious, but there's some calculations involved. We're not going to worry about calculating this quantity, okay? But you should know that the probability of a type 2 error is called beta, okay? So alpha is the first letter of the Greek alphabet. Beta is the second. So type 1 alpha, type 2 beta. Alpha bet, right? So probability of type 2 error. Okay. And then we give a special name to something called 1 minus beta. And this thing is called power. What is power? What's 1 minus anything? The complement, right? Okay, so this would be 1 minus beta is the complement of, huh?
Beta.
Not the complement of beta. Beta is the probability of what? Committing a type 2 error. So 1 minus beta is the complement of committing a type 2 error, or is the probability of
Not committing a type 2
of not committing a type 2 error. Okay, it's not. No, I know you guys are all like probability of alpha. No, okay, alpha itself is a probability. Okay, so power is the probability of not committing a type 2 error. Okay, so this is a logic mind problem. All right. What does it mean? What does it mean not to commit a type 2 error?
See, if H null was not false.
Okay, so think about this and let's talk about it. So type 2 error is you choose not to reject the null, but the null is actually false.
So you choose to reject
When?
when it's not true.
When it's false. When it's false. Dang it. Right. Almost. So close. So close. Okay. So it's probability of not committing a type 2 error. So it's choosing to reject the null when the null is false. Is that something you want to do? That's something you want to do. Okay? When the null is false, you want to reject it. And power is the probability that you're going to make the correct decision. Okay? Power. So the power of a test is how good is this test at correctly rejecting the null when it's supposed to. Okay? So wait, let me just write this down. Probability of correctly rejecting the null hypothesis when you are supposed to. Meaning when the null hypothesis is false. So that is power. Tony, do you have a question?
I thought it would be you choose not to reject the null, but the null is.
Okay, I know what you're saying, all right, but it doesn't work that way. Okay, so beta is the probability of a type 2 error. So you don't have to write this down anybody. I'm just putting this. Okay, the type 2 error is a conditional probability. It's probability of not reject null given null is false. Okay. When I take the complement to this, I don't ever switch the given part. Right? What's right? Probability of A given B. If I do what's the complement to this? This would be equal to the probability of not A given B. Yeah?
But if you are rejecting the null hypothesis, there is no chance that you're committing a type 2 error, because to commit a type 2 error, you're choosing not to reject the H.
Right.
So
So that's right.
it just seems like the 2 would never.
Well, that's why they're complements of each other. So, type 2 error is beta, and the complement to that is, I got like chalk dust in my throat now, is the power, okay? And that's the probability of correctly rejecting the null when you're supposed to reject the null.
So it's kind of like A, like, E given A, so your given is always going to be the reality of whether it
Yeah,
is.
so the given part is the reality. We just don't know what it is, okay? And so we're saying, okay, if this is the reality, what's the probability that I'm going to make this decision? And if this is the reality, what's the probability that this is going to happen? Okay, so there's calculations involved with that. Okay, let's take a short break. We'll come back at 9 o'clock, and then we'll finish this chapter out.